In the 21st century, human beings have achieved great wonders. Today, as a group project for ESTR 1003, we are going to talk about how we took a picture of a black hole. First, as a group member, I will introduce the first part of the whole lecture, while my groupmate Yifan will continue to introduce the second part. For our lecture is divided into four parts. First, introduction. Second is series. And third, basic ideas. And fourth is method. First comes the introduction. For the black hole, before we took a picture of it, it only exists in Einstein theory. But actual novices have never seen the black hole face to face. They only heard of vibrations or gravitational waves from the black hole. But things began to change on April 10, 2017. Actual physicists announced that they had captured the first ever image of the black hole, and this black hole is named M87, which is 55 million light years from our planet. So, on that day, we find the direct evidence of the existence of the black hole. So the theory is about the property of the electromagnetic waves. There are two theories. One is differentiation. The first, let's tell something about differentiation. For the longer the wavelength, the shorter the ability of the wave to travel around obstacles will be. So in theory, we can use those waves with longer wavelengths to find a black hole, for they can travel around millions of obstacles and then reach our Earth. And the second theory is the knowledge of the radio telescope, that is angular resolution. For angular resolution, as we learned in physics class, is equals to lambda over b. So the conclusion is how small a telescope can see, or how small the telescope can tell the difference between two objects depends on two things. One is the wavelength and the other is the physical separation. So to decrease the smallest size we can see from the telescope, we can either reduce the wavelength we observe or we can build a larger telescope. To increase the size of a telescope, let's take an example. For our difficulty we are facing to observe a black hole on our Earth is like observing an orange from the moon on our Earth. But as I saw the picture of the clearest photo we can take from Earth is that this one. For each pixel is 1.5 million oranges. So imagine how large a telescope we need to have it be. For the first method I am going to introduce is why using wavelengths with shorter wavelengths is impractical. For actually, there is advantage of using short wavelengths because there are abundantly amplitude electromagnetic waves released by the black hole, like some gamma waves and X-ray waves, which has extremely shorter wavelengths, and their feature is very obvious. So if we get those shorter wavelengths, we can directly tell that is come from the black hole, and those wavelengths is easier for us human beings to make an image. But there are disadvantages. However, for this phenomenon that electromagnetic wave will derivative from the law of linear propagation after encountering obstacles. For after millions of light years of propagation, the valuable short-wave electromagnetic waves we get on Earth shrinks to zero. For I give you a detailed explanation. Is that we know that in our universe there are small obstacles like dust or small pieces of stones, and bigger obstacles like celestial bodies for like a planet or the star, the sun. If those electromagnetic waves with extremely shorter wavelengths encounter with those obstacles, for the first one, small obstacles and they will result in two severe consequences. The first one is reduction in energy, and the second one is changes in wavelengths. For the first, reduction in energy is easy to explain from it is corresponded to lecture slide 4, page 23 to 42. However, the wavelengths with shorter wavelengths encounter with obstacles, it travels around the obstacles, but together it loses part of its energy. For not need to mention that there are thousands or millions of obstacles that blocks in the way from the black hole to our planet. So it is hard to imagine how weak we can get the electromagnetic waves from our Earth. And the second is due to Einstein's theory, electromagnetic waves also have a momentum. Whenever it encounters with some atom or some small obstacles, it gives part of its energy to those obstacles and resulting in the change in its wavelength, or to say its frequency. So some of them we get must can be noise or something, but they are actually comes from the black hole. So sometimes we just cannot tell them. And for bigger obstacles like celestial bodies, the electromagnetic waves, because it have extremely short wavelengths, so resulting in the extremely weak ability to travel around obstacles. So most of them will be directly absorbed by the bigger obstacles. So according what we have mentioned about, using wavelengths with shorter wavelengths is totally impractical. So that's all about my part, and my teammate Yifan will keep on introducing the practical method we are taking now, and it is actually working. That's all. Thank you for listening.